Lie still for a moment. If you have ever spent a night outside, really outside, far enough from any city that the sky above you was genuinely dark, you will remember what it felt like to look up, not to study the sky, not to identify anything, simply to look. The darkness up there was not empty in the way a ceiling is empty. It had texture, it had depth. Stars at different distances gave the impression of a space you could fall into, slowly, without alarm. That feeling was telling you something true. The sky you were looking at is not a flat surface with lights embedded in it. It is a volume, a three-dimensional arrangement of objects separated by distances so large that the light reaching your eye from the nearest of them began its journey 4 years ago, traveling at a speed that would carry it around the entire Earth 7 times in a single second. The farthest objects you can see with your bare eyes left their sources thousands of years ago, long before any writing system existed, long before any city rose or fell. You were not looking at a picture of the universe. You were receiving its history, delivered across a silence too vast to feel, in the form of light. What you were not seeing was everything else. The darkness between those points of light, the actual majority of what you were looking at, is not simply the absence of stars. It is a specific environment with specific properties, a place as real and as physical as the stars themselves. And it is, by almost any measure, the dominant feature of everything that exists. The bright points are the exceptions. The dark between them is the rule. This is not a frightening idea. It has never been a frightening idea to the people who lived most closely with it. For most of human history, the night sky was not a mystery to be solved. It was a companion. It was the ceiling of every sleeping place that did not have a roof. It was the only clock, the only compass, the only map that worked in every weather, on every ocean, in every desert. People looked up not to be humbled, but to be oriented, to find where they were, what season it was, how long until morning. The darkness was familiar, it was reliable. It had been there every night of every life anyone had ever lived, and it would be there tomorrow night without fail. Tonight, we are going to travel into that darkness, not toward any one star, not on a straight line toward any destination. Outward, steadily, quietly, in the way that a long night naturally moves, through the structure of everything that exists, layer by layer, from the light above your head to the edge of what can be seen, and then a little beyond. The sky is already dark. The distances are already there. We begin. There is an experience that no living person has had, and that nearly every person who lived before the 20th century had every single night, standing outside after dark and seeing the sky as it actually is, not a few dozen stars visible through the sodium glow of a parking lot. Not the faint smear of the Milky Way glimpsed once on a camping trip, pale and tentative. Something you had to tell people was actually there. The full sky, the sky that ancient astronomers catalogued, that Polynesian navigators memorized, that Egyptian priests mapped onto the ceilings of tombs. A sky so dense with stars that the darkness between them seemed almost secondary, a negative space inside something luminous rather than the other way around. Current estimates suggest that roughly 80% of people alive today have never seen this sky. The light from cities reaches so far and scatters so thoroughly that the Milky Way, the pale band of our own galaxy viewed edge-on, containing hundreds of billions of suns, is permanently invisible to most of the human population. This is a recent loss. For 300,000 years before it, the full sky was simply what the night looked like. Think about what that meant for the texture of daily life. There was no experience of going to sleep that did not involve, at some point, being under that sky. Even the most sheltered person, in the most permanent dwelling, spent time outside after dark. Children fell asleep to it. Travelers navigated by it. People who had never thought of themselves as astronomers nonetheless carried a working knowledge of which stars rose when, which ones never set, which ones could be trusted when clouds obscured everything else. The sky was not a spectacle. It was furniture. It was part of the room. And within that familiarity, certain things were noticed. The dark between the stars was not uniform. Some regions of sky were denser, more crowded, shot through with the pale haze of the galactic band. Others were emptier. wide patches of deep black, where no matter how long you looked, there was simply less. The people who spent the most time under that sky, the ones whose work or survival depended on reading it carefully, paid attention to those empty regions too. The darkness was part of the information, long before any telescope existed. Sailors crossing the Pacific used the dark between stars the way a reader uses the white space between words, as structure, as punctuations, as the thing that gives meaning to what surrounds it. They did not know its mass or temperature. They did not have a name for intergalactic space or the cosmic void. They knew only that the sky had shape, that the shape was consistent, and that the dark patches between bright stars held their positions as faithfully as the stars themselves. For 10,000 years, across thousands of open water crossings that no modern navigator would attempt without satellite guidance, this knowledge kept people alive. The darkness was a tool. That steadiness is not a cultural interpretation, it is a physical fact. The geometry of the sky changes on timescales so long that no civilization has ever witnessed more than a small fraction of a single cycle. The stars that Polynesian navigators used to cross the Pacific look essentially the same tonight as they looked 3,000 years ago. The dark patches between them are in essentially the same positions. If a sailor from that tradition were somehow transported to tonight's sky, they would need very little time to orient themselves. The basic structure would be familiar. The darkness would be where it had always been. There is something in that continuity worth resting inside even now. The sky above you tonight, or the sky above wherever you happen to be, even if clouds or cities are hiding most of it, is the same sky, the same darkness. The photons that fell on a navigator standing at the bow of a double-hulled voyaging canoe somewhere in the Pacific, reading the stars to find an island no European sailor had yet charted, and the photons falling now on the buildings and trees outside your window are following the same paths, from the same sources, across the same distances. The light did not change, the dark did not change. What changed is what we do when the light arrives, what instruments we hold up to it, what questions we have learned to ask. And yet even now, with the most precise instruments ever built, with space telescopes that have gathered light from objects more than 13 billion light-years away, the darkness keeps its character. It is not smaller than it seemed to the navigator, it is larger. Every instrument we have built to study the night sky has confirmed the same basic finding in more and more precise detail. The darkness is not a background, it is the thing itself. The stars and galaxies are the minority. The void is the majority. The navigator reading the dark between the Pleiades and the Southern Cross was, without knowing it, reading the edge of the largest structure in the observable universe. They were right to pay attention to it. Tonight, that attention becomes the journey. We are going to move outward from this sky, from the familiar band of the Milky Way, from the nearest handful of stars close enough to have names, from the neighborhood of space that human beings have charted and catalogued over the last few hundred years of careful observation. We are going to move from here to there, in the direction of the dark, toward the places where the darkness is not merely the space between stars, but something older and deeper and quieter than anything a star has ever illuminated. The navigator did not need to understand the void to use the sky, but we have been given instruments that let us look more carefully. And when you look more carefully at the dark, you find that it has structure, that the emptiness between galaxies is organized, patterned, built from processes that began within the first fraction of a second of the universe's existence, and have been playing out slowly ever since, growing quieter by the era, patient in a way that nothing made of matter can quite manage. That structure is where tonight takes us, not into alarm, not into a darkness that is threatening or final, into the same darkness that has been above every sleeping person who ever lived, now seen from a little farther out, with a little more of its architecture visible. The sky is there. The dark between its lights is patient. We continue before anything else, before we move outward toward the space between galaxies or the edges of the observable universe. We need to understand the size of the place we are leaving. Most people have a rough idea that the Milky Way is large. They have seen the phrase billions of stars, often enough that it has lost its impact, the way a number too large to visualize stops being a number and becomes a noise. But the Milky Way is not merely a large collection of stars. It is a specific physical object with dimensions that, once you sit with them honestly, change the way the rest of this journey feels. The Milky Way spans somewhere between 100,000 and 200,000 light years from edge to edge. The variation in that estimate comes from how you define the galaxy's boundary, whether you count only the dense disk of stars visible in photographs, or include the fainter outer arms, the extended stellar halo, the dark matter envelope that extends well beyond any visible structure. At the conservative end of that range, 100,000 light years. Take the speed of light, 186,000 miles per second, a speed that would carry a beam from New York to Los Angeles and back roughly 30 times in the duration of a single heartbeat, and ask how long it takes to cross the galaxy at that speed. 100,000 years. A beam of light, the fastest thing that physics permits, needs the same length of time to cross our galaxy from one side to the other as separates us from the moment the first anatomically modern humans began migrating out of Africa. When the light now arriving from the far edge of the Milky Way began its journey, our species was still entirely on one continent, using stone tools, speaking languages that left no written record. The light was already halfway through its crossing when the last ice age ended. It was 3/4 of the way across when the first cities appeared in Mesopotamia. It arrived tonight. That is what a single galaxy looks like in time. In space, the picture is proportionally staggering. Our Sun sits approximately 26,000 light years from the galactic center, not in the middle, and not at the edge, but somewhere in the middle of one of the spiral arms, in a fairly ordinary region of fairly ordinary stellar density. There is nothing special about our location within the galaxy, in the way that there is nothing special about the particular house you grew up in, along a particular street in a particular city. We are simply here, in the place where one unremarkable star happened to form about 4.5 billion years ago. From our position, the galactic center is 26,000 light years away. The nearest edge of the galaxy in the opposite direction is roughly 50,000 light years. In every direction along the plane of the disk, you would travel for thousands of light years before reaching the galaxy's edge, and then thousands more before you were truly clear of the faint outer structures. The disk itself, the flat, rotating structure where most of the Milky Way's stars live, is only about 1,000 light years thick in our neighborhood. We live inside a pancake, 1,000 light years tall and 100,000 light years wide. Orbiting a center we cannot see directly because 26,000 light years of gas and dust sit between us and it. The number of stars in this structure runs somewhere between 200 billion and 400 billion. Current estimates lean toward the higher end of that range, as increasingly sensitive surveys continue to find faint stars at the galaxy's edges that earlier observations missed. 200 billion is the conservative figure. It is still a number the human mind cannot genuinely hold. If you tried to count to 200 billion at a rate of one number per second, without sleeping or pausing, it would take more than 6,000 years. The count would have begun before the earliest writing systems were developed and would still be in progress today. Each of those stars is a sun. Many of them, the current consensus says most of them, have planets. Some of those planets orbit at distances where liquid water could exist on a rocky surface. Some of those rocky surfaces may carry the chemistry that on our world, given enough time, eventually asked questions about the size of the galaxy it lived in. The Milky Way is not one of the largest galaxies in the observable universe. It is not even close to the largest. It is a mid-sized spiral, respectable but not exceptional, in a region of the universe that contains many galaxies of similar dimensions. There are galaxies with 10 times as many stars, extended over proportionally greater distances. There are galaxy clusters containing thousands of galaxies like ours, packed into a shared gravitational system. that spans tens of millions of light years. By the standards of the cosmic web, the Milky Way is neither impressive nor embarrassing. It is simply one of a very large number of similar structures. But for the purposes of understanding what it means to leave it, to step outside its gravitational influence and enter the space between galaxies, the Milky Way's size matters. Because the space we are about to describe is not merely larger than the Milky Way, it is larger than the Milky Way by the same kind of factor that the Milky Way is larger than the distance from here to the nearest star. In ancient Egypt, a scribe watching from a rooftop on a clear night would have seen essentially the same band of the Milky Way arching overhead that a person can see tonight from any genuinely dark location. The light reaching that scribe's eyes from the galactic center had already been traveling for 26,000 years. It passed through the period of human history in which all written language was invented, passed through it silently, on a trajectory that had nothing to do with what was happening beneath it. The geometry has not changed, the distances have not shortened. Only the watchers have changed, and even then, only slightly. We carry different instruments and different names for what we see. The light we receive is the same light, from the same sources, crossing the same distances. Entire civilizations rose and fell in the time a single photon needed to cross from one side of our galaxy to the other. The Roman Empire, the Han Dynasty, the Aztec Empire, the British Empire, all of it, the full arc of complex urban human civilization from the first cities to the present, occupies less than half of 1% of the time it takes light to make that crossing. The galaxy is not merely old relative to a human life. It is old relative to civilization itself, by a factor that makes civilization feel like a recent footnote. This is the object we are leaving behind. When we move outward from the Milky Way, we are not stepping from a small room into a large room. We are stepping from an object whose crossing time exceeds all of recorded history into a space where the distances between objects are measured in multiples of that crossing time. The intergalactic void does not begin gradually. It begins at the edge of our galaxy's gravitational influence, not far, by cosmic standards, from where we already are. And then it simply continues in every direction, for distances that require a different kind of attention. The galaxy is behind us now. Or rather, we are inside it. We will always be inside it, in the only sense that practically matters. But we are going to look outward, past its edges, into what comes next. The next object is close, as these things go. The photons from it have been traveling for a much shorter time than the photons crossing our galaxy. They left their source before humans built the pyramids, before any civilization we know by name, before agriculture. But they are arriving now, and they are visible on a clear night in the southern sky. If you know where to look, we are going to find them. The two nearest galaxies to our own are not dramatic objects. They do not appear in most casual sky photographs. They do not feature in the lists of objects that amateur telescopes are pointed at on clear nights in the northern hemisphere. They are visible to the bare eye only from the southern half of the world, and even there, only on dark nights away from any city, and only if you know roughly where to look. They appear as detached patches of the Milky Way, two blurry luminous clouds sitting just outside the main band of our galaxy, small and pale and easy to overlook. Their names are the Large Magellanic Cloud and the Small Magellanic Cloud. They are not clouds, they are galaxies. The Large Magellanic Cloud sits approximately 160,000 light-years from Earth. It contains somewhere between 10 and 30 billion stars, smaller than our galaxy by an order of magnitude, but a substantial structure in its own right, with its own star-forming regions, its own clusters of young blue stars, its own ancient red giants that have been burning since the universe was young. It orbits the Milky Way the way a moon orbits a planet, pulled by the same gravity that keeps our sun in its circular path around the galactic center. The relationship is not equal. The Milky Way is roughly 10 times more massive. The Large Magellanic Cloud is a satellite, slowly orbiting its larger companion on a path that will eventually, over billions of years, bring it into a gravitational merger. The Small Magellanic Cloud is slightly farther, roughly 200,000 light-years away. It contains a few billion stars, irregular in shape, visibly disrupted by the tidal forces our galaxy exerts on it. A bridge of gas connects the two Magellanic Clouds to each other and to the Milky Way, a structure called the Magellanic Stream, a trail of material drawn out by gravitational interaction, stretching across 150 degrees of sky, 160,000 light-years. That is where the nearest galaxy sits. The light arriving from the large Magellanic Cloud tonight left its source 160,000 years ago. At that moment, our species was already anatomically modern. The people whose descendants would eventually develop agriculture, build cities, and invent telescopes to study this very light were already alive, living, sleeping, looking at a sky that already contained the object they were looking at, with no instruments, no understanding of what it was, and no knowledge that it was any different from the rest of the Milky Way band it appeared to adjoin. The light was already in transit. It had been traveling for most of human prehistory, before anyone had any idea it was coming. This is what intergalactic distance begins to mean. Not a single dramatic leap into the unknown, but a slow accumulation of time. Light crossing space during intervals that human history cannot easily hold. And the Magellanic Clouds are the closest case, the nearest examples, the shortest intergalactic distances we know. Beyond them, the gaps grow. The Andromeda Galaxy, the nearest large spiral galaxy to our own, sits approximately 2.5 million light-years away. The light reaching your eyes from Andromeda on a clear autumn night in the northern hemisphere left its source before the genus Homo existed on Earth, the earliest members of our evolutionary lineage recognizable as human. Not yet our species, but related, upright walking, stone tool using ancestors, were not yet born when that light began its crossing. The entire history of human evolution, every anatomical change, every cognitive development, every migration and adaptation that produced the species now lying here, listening to this, all of it happened during the transit of that light. It left before us. It arrives now. Andromeda contains approximately 1 trillion stars. Its disk stretches across roughly 260,000 light-years. A revised mosaic, assembled from over 600 overlapping observations, released in early 2025, resolved approximately 200 million individual stars and still captured only a fraction of the galaxy's total stellar population. It is a complete world in itself, a gravitational empire containing thousands of star clusters, billions of planetary systems, a supermassive black hole at its center with a mass more than 100 million times that of our Sun, and it is close. By the standards of what we are about to discuss, 2.5 million light-years is close. Andromeda is our nearest large neighbor, our most immediate galactic companion. It is, along with our own Milky Way, one of the 2 dominant members of a loose family of galaxies known as the Local Group. The Local Group, as of the most carefully revised catalogues, contains approximately 142 confirmed members. Most of them are small, dwarf galaxy containing only a few billion, or even a few hundred million, stars. Most orbit either the Milky Way or Andromeda as satellites bound by gravity, slowly circling their larger companions the way the Magellanic Clouds circle ours. A handful are independent, small isolated galaxies drifting through the shared gravitational field of both dominant spirals without being clearly attached to either. The full diameter of the Local Group, from its outermost confirmed members on one side to the outermost on the other, spans approximately 10 million light-years. That is our neighborhood. The gravitationally bound family that contains everything we will ever be able to call home 10 million light-years is roughly 100 times the diameter of the Milky Way. Think about that ratio carefully. If our galaxy were a house, the nearest house would be approximately 100 house lengths away. The entire neighborhood, every structure we are gravitationally bound to, every galaxy that could theoretically be reached, given sufficient time and technology, would extend across a volume 100 times the size of our home in every direction. And between those houses, between the Milky Way and its satellites, between us and Andromeda and Triangulum, and the scattered dwarfs in between, there is almost nothing. That almost nothing has a specific character: interstellar space. The space between stars within the Milky Way already qualifies as a profound vacuum. A typical cubic meter of interstellar gas in the relatively dense parts of our galaxy contains roughly 1 million hydrogen atoms. By any earthly standard, that is extraordinarily empty. The air in the room where you are now contains something in the vicinity of 25 trillion molecules per cubic meter. Interstellar space is millions of times emptier than that. And yet, intergalactic space, space between the galaxies of the local group, is roughly 1 million times emptier than interstellar space, 1 atom per cubic meter. In some regions, less. If you extended your arm into intergalactic space and swept it slowly through a volume the size of a small house, you would not, in all likelihood, touch a single atom. The material that does exist there, a thin, hot plasma called the warm-hot intergalactic medium, is distributed so sparsely that despite technically being present, it registers as indistinguishable from a perfect vacuum at any scale a human body could experience. The void between galaxies is not the absence of something that was there before. It is a physical environment in its own right, with its own properties, its own temperature, its own identity. The temperature of that near vacuum, incidentally, is millions of degrees. This sounds alarming until you understand that temperature describes the average kinetic energy of individual particles, not the rate at which heat can transfer from one object to another. With so few particles per cubic meter, there is essentially no heat transfer. A human being floating in intergalactic space would not be warmed by the technically scorching plasma around them. They would radiate heat into the void and freeze. The void is simultaneously hot and cold, depending on which definition you use. And this contradiction is one of the ways it resists ordinary description. This is the environment separating the galaxies of the local group. Not a corridor, not a passage, not a medium in the sense that an ocean is a medium, where something can propagate from one shore to the other, where the space between carries what the destinations send. An absence so thorough that even calling it space slightly overstates its contents. The galaxies float in it, pulled toward each other by gravity, across distances that light takes millions of years to cross, separated by a near-perfect vacuum that extends without interruption for hundreds of thousands of light years between even the closest neighbors. Right now, as you rest, light from the Andromeda galaxy is completing a journey that began before any member of our genus existed. It left its source 2.5 million years ago, not as a deliberate signal, not as a message, but simply as the natural consequence of hydrogen burning in a star, producing photons that traveled outward in every direction at once. Most of those photons went nowhere in particular. A small fraction happened to travel in the direction of our solar system. That fraction has been crossing intergalactic space ever since, across the near-perfect vacuum, across the interval during which all of human evolution unfolded. And it arrives now, at this moment, while you are still. It has been traveling the entire time you have existed, and the entire time every ancestor you have ever had existed, and for millions of years before any of them were born. It arrives anyway. That is what light does. Beyond the local group, the distances begin to scale again, and the nature of what fills the space between structures changes in ways that require a different kind of attention. We are not yet done with the local group. We are still inside it, in the sense that everything in the local group is gravitationally bound. But the next stage of the journey requires looking at the space surrounding our neighborhood from the outside and understanding what kind of structure that neighborhood sits within. The local group is not an island in an otherwise uniform sea of evenly distributed matter. It sits on the edge of something, a thin filament of galaxies and dark matter that extends outward from our neighborhood in the direction of a gravitational attractor our galaxy is slowly, imperceptibly moving toward. The filament connects to other filaments. Those filaments bound enormous empty regions on either side. The structure, seen from far enough outside, resembles nothing so much as the web a spider spins. Thin strands of material connecting nodes where mass has concentrated, and between the strands, nothing. This is the architecture of everything. We are going to move out to a scale where that architecture becomes visible. Pull back far enough, and the universe stops looking like a collection of galaxies. From the scale of the local group, 10 million light-years across, a neighborhood of 140-odd galaxies. Pull back to the scale of 100 million light-years, then 500 million, then a billion. At these distances, individual galaxies stop being distinguishable objects and start being dots, the way cities become dots when you look at the Earth from orbit. And the pattern those dots form is unlike anything visible at smaller scales. It is a web. Astronomers have been mapping this structure for decades, using surveys that measure the precise positions and distances of hundreds of thousands of galaxies across billions of light-years of space. The pattern that emerges from those surveys has a name, the cosmic web, and it consists of 4 distinct types of structure arranged in a specific relationship to each other. Nodes, dense concentrations of matter, usually galaxy clusters, where multiple streams of material have been converging for billions of years. These are the brightest, most massive objects in the visible universe. Collections of thousands of galaxies, all bound together by shared gravity, their combined mass equivalent to quadrillions of suns. Filaments, long, thin threads of galaxies and gas, connecting one node to the next. Filaments can stretch across hundreds of millions of light-years, while remaining only 20 million light-years or so in width. They are disproportionately long and narrow, more like threads than ropes, more like rivers than highways, and they carry galaxies along them the way a current carries flotsam, slowly, over timescales measured in billions of years. Walls, flat sheets of galaxies at the intersections of multiple filaments, less concentrated than clusters, more diffuse than filaments. They extend across hundreds of millions of light-years, while remaining relatively thin in the direction perpendicular to their plane. And then there are the voids. Voids are not holes in the cosmic web. They are the cosmic web, in the same sense that the white space on this page is not an absence of text, but a structural feature of what text looks like when it is arranged to be readable. The web has shape because the voids have shape. The filaments define their own boundaries by defining the boundaries of the emptiness on either side. Take away the voids, and the filaments would have nothing to be thin against. Typical voids measure between 30 and 300 million light-years across. The largest confirmed supervoids exceed that, 300 million light-years in diameter, volumes of space so large that the Milky Way would sit somewhere in their interior with hundreds of millions of light-years of near emptiness in every direction. Together, voids account for approximately 80% of the total volume of the observable universe. 80%. The universe by volume is mostly void. The galaxies, all 2 trillion of them, occupy the remaining 20%, and most of that 20% is not solid matter, but the thin filaments and walls within which galaxies are strung like beads. The dense nodes where galaxy clusters live are a small fraction of even that 20%. The actual solid matter, the stars and planets, and everything made of atoms, is a vanishingly thin residue clinging to the surfaces of an architecture built primarily from emptiness. One specific void has a name that matters tonight. In 1981, a team of astronomers conducting a survey of galactic positions noticed something unusual in a particular region of sky. They expected to find galaxies at the distances they were measuring. They found almost none. The region was roughly spherical, roughly 330 million light-years in diameter, and it contained approximately 60 galaxies, where the cosmic average would predict around 2,000. Its existence had to be confirmed multiple times before the survey team was confident. The data was not a systematic error. The emptiness was real. The region is called the Boötes Void, after the constellation in whose direction it sits, approximately 700 million light-years from Earth. Stand inside the Boötes Void, imagined as a thought experiment, and look outward in any direction. The nearest galaxies are not millions of light-years away. They are tens of millions. in most directions hundreds of millions. A civilization sitting at the center of the Boötes Void, on a planet orbiting a star in one of the 60 or so galaxies that do exist within it, would look outward and see a sky almost completely dark. Not the darkness of a cloudy night, where you know the stars are hidden. An absolute dark, structural and permanent, extending without interruption to a horizon so far away that the light from the nearest external galaxies would require tens of millions of years to reach them. That civilization, if it developed astronomy, would build telescopes and point them outward and find nothing. They would look harder and find still nothing. Their most powerful instruments would eventually begin to detect faint, distant objects, but only after pushing sensitivity to extremes that would take them centuries or millennia to achieve. And when they finally mapped what was out there, they would find a wall of galaxies at a distance so great it would seem unbelievable. The edge of their void, the nearest filament, the border between the emptiness they inhabited and the inhabited structure beyond, they might conclude, not unreasonably, that the universe was simply empty, that their galaxy was alone, that the lights they detected at the edge of their instruments' reach were anomalies rather than the edge of something vast and populated. We know they would be wrong, but they would have no way of knowing that from inside. The Boötes Void is not unique. It is one of many such regions. It happens to be among the largest confirmed, and it has a name, but the cosmic web is riddled with voids of every size. Our own galaxy appears to sit inside a structure called the Boötes Void, a region of below-average density approximately 2 billion light-years across, within which the density of matter runs roughly 20% lower than the cosmic average. The Boötes Void is not as empty as the Boötes Void. It still contains many thousands of galaxies, but it is large enough and empty enough that it measurably affects the motion of our galaxy, pushing us away from its center at hundreds of thousands of miles per hour. A gentle sustained nudge from the relative emptiness behind us toward the denser structures ahead. We are, in other words, inside a void, a mild one, as voids go, but a void nonetheless. The cosmic web surrounds us at a distance. The nearest major galaxy cluster, the Virgo cluster, sits roughly 54 million light-years away on the nearest filament of the web. The light arriving from Virgo tonight left its source before the first primates appeared on Earth. The structure of the cosmic web was not designed. It was not arranged by any process that had an outcome in mind. It arose from the smallest possible initial differences, quantum fluctuations in the density of the infant universe, variations of roughly 1 part in 100,000 in the distribution of matter in the first fraction of a second after the Big Bang. Some regions had slightly more matter. Gravity pulled more matter toward them. The surrounding regions became slightly less dense as their matter drained away. Over billions of years, those initial tiny differences amplified into the dramatic architecture of voids and filaments we observe today. The voids exist because the filaments drained them. The filaments are dense because the voids fed them. The structure and the emptiness are the same process, viewed from 2 different positions. Every grandmother who ever pointed upward on a clear night, every child who ever asked what the dark patches were between the stars, every sailor who read the sky as a tool and trusted the dark as much as the light. They were all looking out across this structure, unaware of its full dimensions. The wandering did not require knowledge of the cosmic web. The web was there regardless, organizing the darkness into patterns too large for any single human lifetime to perceive, present in every direction any eye has ever pointed upward. The dark between the Pleiades and the Southern Cross that a Polynesian navigator used as a reference. It was a small sample of the void, the dark above the Sahara that a desert traveler used to orient by. Another sample, every patch of dark sky that any person has ever looked into has been a window onto the same structure, an architecture of near emptiness, built over billions of years from the smallest possible starting conditions, containing within it the thin threads of light along which all the galaxies we know have organized themselves. The web is vast. 80% of it, by volume, is the emptiness that shapes the rest. And the emptiness is not static. The voids are growing. Dark energy, the mysterious force that drives the accelerating expansion of space, operates most powerfully where gravity is weakest. Inside dense clusters and filaments, local gravity slows the expansion to a near halt. The galaxies in those regions remain bound, remain neighbors, remain structurally connected. But inside the voids, where there is almost nothing to resist expansion, dark energy pushes space apart with essentially nothing to push back against. The voids expand faster than the cosmic average. They grow larger. They push the filaments on their edges farther apart. They swallow additional volume with every passing era. The architecture of the universe is not permanent. It is a phase, a specific arrangement of matter that exists because the universe is still young enough for gravity to compete with expansion. That competition is ongoing, and in the densest regions, gravity is winning locally. But in the voids and at the largest scales, expansion is winning. The web is thinning. The filaments are stretching. The connections between clusters are becoming more tenuous with every billion years that passes. Where we are now, inside the web, inside a mild void, part of a local group that is gravitationally bound and will remain so, is a relatively sheltered position. We are inside one of the structures that local gravity protects, but the universe beyond our gravitational family is moving away, and it is moving away faster every year. We are going to follow that motion outward into what it implies. The next step is not more distance. It is time, the deep future, that the current motion of the cosmos makes inevitable, and what that future looks like for the one structure we will always call home. The Milky Way and the Andromeda galaxy have been falling toward each other for most of the universe's history. The pull between them is gravity, the same force that holds the moon in its orbit around Earth, that keeps Earth circling the sun, that bends light and holds stars in their paths around the galactic center. At the scale of 2.5 million light-years, gravity is subtle. It does not announce itself, but it has been operating without pause since both galaxies formed and the measurement of Andromeda's approach, refined over decades of spectroscopic observation, confirmed by proper motion data from space-based observatories, is unambiguous. The two galaxies are closing the distance between them. Analysis published in 2026, incorporating the most precise proper motion measurements available, places the probability of a merger within the next 10 billion years at approximately 90%, with a median collision time around 6.5 billion years from now. The merger itself will not be a single event. It will be a process, a series of gravitational passes, each one drawing the two galaxies closer and more disrupted, stretching out over hundreds of millions of years before the final coalescence. The stars within both galaxies are so widely spaced that most of them will pass through the merger without colliding with any other star. It is not a collision in the ordinary sense. It is a slow interpenetration. Two vast gravitational systems flowing through each other, reshaping each other, eventually settling into a single new configuration. Astronomers have already given a name to the structure that will eventually result. It is called Milkomeda, an informal label for the merged elliptical galaxy that the Milky Way and Andromeda will form after the coalescence is complete. Milkomeda will be a different kind of object from either of its parents. The elegant spiral arms of both current galaxies will be gone, shredded by the tidal forces of the merger and dispersed into the random stellar orbits characteristic of elliptical galaxies. The combined structure will contain the stellar populations of both current galaxies, along with every dwarf galaxy currently orbiting either of them, assembled into a single enormous system with a massive central core and a diffuse outer halo of stars on orbits tilted at every possible angle to every other. Milkomeda will be home. Not for us. We exist only now, in the spiral arm of the Milky Way 4,600 years after the Egyptian Old Kingdom collapsed. But for whatever comes after us, for whatever minds might exist on whatever world's orbit, whatever stars have formed from whatever gas has condensed, in whatever spiral arm is still forming stars in 6 billion years, Milkomeda will simply be the sky, the merged galaxy, the entire visible structure of stars, And the sky beyond Milkomeda's edge in the far future will be something that no one now alive has ever experienced from the inside. Dark energy, the force driving the accelerating expansion of space, ensures that every galaxy not gravitationally bound to the local group will continue to recede, not at a fixed speed, but at an accelerating one carried by the expansion of space itself. Today, the nearest large galaxy cluster, the Virgo cluster, is 54 million light-years away. It is not bound to us, it is receding. The universe's expansion is carrying it farther with every passing year, and because expansion accelerates, it will be moving faster next century than it is today, and faster still the century after that. There is a distance at which a receding galaxy's recession velocity, carried by the expansion of space, equals the speed of light. Beyond that distance, light emitted toward us today will never reach us. The expanding space between us and the source stretches the light's path faster than the light can travel it. That boundary is called the cosmic event horizon, and it currently sits at approximately 16 to 18 billion light-years from Earth. Of the roughly 2 trillion galaxies in the observable universe, approximately 94% are already beyond that horizon. Their light is still arriving. The photons we see from them left their sources when the universe was smaller, when the distances were short enough for the light to begin its journey before expansion carried those galaxies past the reachable zone. But those galaxies, as they exist right now, are gone, permanently beyond contact. Within 100 to 150 billion years, current cosmological models project every galaxy outside the local group will have crossed permanently beyond the event horizon. The Virgo cluster will be gone. The Komar cluster will be gone. Every filament and wall of the cosmic web, every void boundary, every structure that makes the large-scale universe legible, all of it will have receded beyond the point where any signal sent at any speed could cross the gap. Milkomeda will be alone. The merged structure will contain its trillion-odd stars, its billions of planetary systems, whatever life or intelligence persists within it, and the complete memory of everything the Milky Way and Andromeda ever were. And it will be surrounded, in every direction, by a darkness that contains nothing detectable. No other galaxies, no cosmic microwave background. That faint afterglow of the Big Bang, still faintly detectable today, will have redshifted to wavelengths so long and an intensity so diluted that no conceivable instrument could recover it from the noise floor of a cooling universe. No trace of the cosmic web. No evidence that the universe ever contained anything, except the structure they are already inside. The pace of those future processes is slow in a way that resists any urgency now. 6 billion years is longer than our sun has been burning. 100 billion years is roughly 7 times the current age of the universe. These are not intervals that bear on anything in the present or the near future. They are the natural consequence of the physics that governs the largest scales of reality, playing out at their own pace, indifferent to the calendar of any civilization that might happen to be present for some small fraction of the unfolding. There is something in that pace, that particular quality of astronomical slowness, that has always been available as a kind of rest. The processes playing out in the cosmic web and the deep future do not require anything of the present. They do not hurry, they do not announce themselves, they proceed with the same measured continuity that light proceeds, not because they are patient in any conscious sense, but because patience is simply the natural character of very slow things. The universe does not know it is expanding. The galaxies do not know they are receding. The void does not know it is growing. The future structure of Milkomeda has no awareness of the merger that will create it. All of it proceeds without witness, without urgency, without the possibility of being rushed. This quality, the absolute unhurriedness of cosmological process, is something the darkness has always offered. We are not done with the dark. One more layer remains before we return to where we started. There is a fact about this moment in cosmic history that is easy to miss. We happen to live at the one time in the universe's existence when the evidence of everything is still visible. The cosmic microwave background, the faint, cold afterglow of the Big Bang, the oldest light in the universe, emitted 380,000 years after the beginning and traveling ever since, is still detectable. The precise instruments aboard space observatories can still map its temperature variations, still read in its patterns the initial conditions from which everything else arose. It is old, and it is faint, and it is getting fainter with every billion years that passes. But it is there, it is still arriving. A sufficiently sensitive instrument, pointed in any direction, can still receive it. The large-scale structure of the cosmic web, the filaments and walls and voids that required billions of years of gravitational work to build, is still intact enough to be mapped. The Virgo cluster is still detectable. The Boötes Void is still a measurable feature of the galaxy distribution. The connections between our local group and the surrounding structure are still legible in the data. The universe's architecture, the full record of everything gravity has done since the first quantum fluctuations seeded its development, is still present in the sky, distributed across 13 billion light-years of visible volume, waiting for instruments sensitive enough to read it. This will not always be true. In the far future, inside Milkomeda, with the local group merged and the rest of the universe beyond the event horizon, an astronomer will look outward and find none of this. The cosmic microwave background will have redshifted to wavelengths far too long to detect. The distant galaxies will be gone, not destroyed, but carried past the horizon of reachability by expansion, their light never to arrive. The large-scale structure will be invisible, not because it no longer exists in principle, but because the evidence of it will have traveled beyond any instrument's reach. The universe will look to that future observer like a single galaxy floating in featureless darkness. That observer will be intelligent. They may be highly intelligent. A civilization of extraordinary sophistication with mathematics and physics of great depth, and yet they will not be able to discover what we know. Not because they are less capable than we are, because the evidence will no longer be available to them. The data we use to determine the age of the universe, its large-scale structure, its origin in a hot, dense state, that data exists because we live early enough to receive it. It is a temporary gift. The universe offered it briefly, and it will take it back. Perhaps this is what it means to exist at a particular moment. Not every moment in the universe's history offers the same view. In the very early universe, the cosmic microwave background hadn't been emitted yet. The web hadn't formed. There was nothing to map. In the very distant future, the evidence will be gone. The readable record of cosmic history exists only in a window, a specific interval during which the universe is old enough to have built its structure and young enough not to have erased its own evidence. We are inside that window. We happen to be here now, at the one era when the full story is still legible. That is not an argument for urgency. The evidence is not disappearing on any timescale that the present moment needs to accommodate. The window is still billions of years wide. The cosmic microwave background will still be detectable for longer than the Earth has existed. The distant galaxies will not cross the event horizon for tens of billions of years. There is no rush. Nothing is ending. But there is something quiet and worth attending to in the knowledge that the sky above contains a record that will not always be there. That the darkness, which has seemed simply dark for all of human history, carries within it the faint statistical signal of the Big Bang, still arriving, still readable, still available to anyone who builds an instrument precise enough to